In this video, I want to review a large number of examples of integral domains that are not fields that we've developed throughout the semester. And I want to do this because as we move into Chapter 18, there are a fair number of very dense-looking theorems. And in order to make sense out of what these theorems say, it helps to have some specific examples. So I want to start with remembering what an integral domain itself is. An integral domain, of course, is a commutative ring with a multiplicative identity that has no zero divisors. And saying that it's not a field means some of the non-zero elements do not have multiplicative inverses. The quintessential example of an integral domain that is not a field is the set of integers under its addition and multiplication. And then after we studied that particular integral domain, we found a bunch of integral domains that were in some sense based on it. The first one was the Gaussian integers, which we wrote as z square bracket I, z adjoined with I. And this was simply the set of a plus bi, where I squared was equal to -1, and a and b were pulled from the set of integers. And it turned out that the Gaussian integers are a subring of the complex numbers under their addition and multiplication. We also looked at integral domains that looked like z adjoined with the square root of 2, and this was the set a plus b times the square root of 2, where a and b were pulled from the integers, and this is a subset of the real numbers, and it is a subring under the same addition and multiplication that you have inside the set of real numbers. You can also combine these two ideas together and look at something like z adjoined with the square root of 3 times I. That would be the set of a plus b times the square root of 3i, where a and b are inside the set of integers, and I squared, of course, is -1. And this again would be another subring of the complex numbers under its multiplication. And in all of these examples, the fact that the set formed an integral domain was because it formed a subring of a commutative ring with identity that had no zero divisors, and the 1 in the big ring belonged to the subring. And that, in fact, gave us a basic important theorem about how we can get integral domains in certain kinds of ways. So we had some theorems that looked like the following. If D is an integral domain, and R is a subring of D, then clearly R is going to be a domain, because R cannot have any zero divisors since D has no zero divisors. And a very basic corollary, if the 1 inside the domain belongs to my subring, then my subring is actually going to be an integral domain. And another corollary to this theorem is that if my domain is actually a field, and R is a subring of my field, and the 1 inside the field is an element of my subring, then my subring is an integral domain. And we had another example on the last problem set where we were using this idea to show that it was actually an integral domain, and I kind of want to look at that particular example of an integral domain as well. On the last problem set, you looked at the ring of integers localized at P, and the ring of integers localized at P is the set of fractions a over b such that a and b, of course, are inside the integers. B is not 0. And the GCD of b and our prime p is known to be 1. Now, what this really means is that when we reduce this fraction down into lowest terms, that in lowest terms, b is not going to have any multiples of p in it. In other words, essentially we can say that a over b belongs to this localized ring when p does not divide b. So if I let p equal 5, then 1/5 is not going to belong to this particular localized ring, but something like 5/7 will belong to this localized ring. And it turns out that the operation that you use for this particular thing is the same operation of addition and multiplication that the rationals use. So this is a subring of the rationals under their arithmetic, and hence this guy is a domain. And since 1 can be written as 1 over 1, and the GCD of p and 1 is equal to 1, that says 1 does belong to this particular localized ring, and that's enough to say that the localized ring is an integral domain. Now we have one more rich set of examples of integral domains that are not fields, and those are our polynomial rings. And so I want to also look at the polynomial rings. So polynomial rings. If I take D being an integral domain, and let me write that word where it's more readable, then d square bracket x is the set of polynomials in x with coefficients inside our domain D, and this particular set, under ordinary polynomial addition and multiplication, is an integral domain. And it's pretty easy to see that. We saw that in the previous video. Essentially, it boils down to if p of x is an nth degree polynomial and q of x is an mth degree polynomial, let's say this is b sub m times x to the m, then p times q is going to start off with an times b m times x to the n plus m and have lots of lower order terms. But the important thing is that this leading coefficient is not equal to 0 since D is a domain, and that says that this polynomial is not the zero polynomial. And so that's enough to say that any ring of polynomials where the coefficients are drawn from a domain is itself an integral domain. There's an important consequence of this. If f is any of our fields, then f square bracket x is going to be a domain, is going to be an integral domain. And what that means is that things like q square bracket x, r square bracket x, um, complex numbers square bracket x, the integers square bracket x, and the finite fields zp square bracket x, these are all integral domains. But it's also important to note that this idea that the leading coefficients are never going to kill each other off allows us to say that this idea generalizes. So if we look at something like q square bracket x comma y, this would be all polynomials in the two variables x and y with rational coefficients. Well, it turns out that if I look at ordinary multiplication and addition, in other words, if I look at this set of polynomials in x and y under polynomial addition and polynomial multiplication, this is still going to be an integral domain. And the idea generalizes. If F is any field or D is any integral domain, then you can have as many variables as you want for your polynomials. So f square bracket x1 through n and d square bracket x1 through n are both integral domains. And none of these integral domains that we've looked at in this video happen to be fields, because they all have some element that does not have a multiplicative inverse. And we'll look at that in later videos at some point.